You know, people ask me all the time, why do magnets work? And I have to tell you something right off the bat. I cannot give you a satisfactory answer that you will feel good about because the answer depends entirely on what you already know, what you already accept as reasonable, and that is the whole problem with explaining magnetism or really explaining anything at all in physics. Let me tell you what I mean by that. When you ask why magnets attract each other, you are really asking me to explain this phenomenon in terms of something else you already understand, something familiar, something that does not need explanation. But here is the rub: what is familiar to you, what counts as a satisfactory explanation that depends entirely on your experience, on what you have been trained to accept as obvious. If I tell you that magnets attract because of magnetic forces, you might say, well, that is not an explanation at all. That is just giving it a name, and you would be absolutely right. But if I try to go deeper, if I try to tell you that it has to do with moving electric charges, with electron spins, with quantum mechanical exchange interactions, then you say, wait a minute, I do not understand those things either. So how can you explain magnets in terms of things I understand even less? This is the fundamental problem. I cannot explain magnetism in terms of anything else you are familiar with, because magnetism is not like anything else you are familiar with. It is a basic fact of nature. It is one of the fundamental forces, and at some point you just have to accept it as given, as something that simply is. Now you might say, well, surely there must be some mechanism, some little gears and wheels turning inside the magnet that make it work. But that is exactly the wrong way to think about it. Nature does not work like a Victorian clockwork machine with little parts pushing and pulling on each other in ways we can visualize. Nature, at its most fundamental level, is utterly strange, completely alien to our everyday intuition, and magnets are actually one of the gentlest introductions to just how weird things really are. Let me try a different approach. Let me tell you what we do know about magnets, what we can measure, what we can calculate, and maybe you will start to see why the usual kinds of explanations just do not work here. First thing, magnets have two poles, north and south, and like poles repel while opposite poles attract. That is an experimental fact. You can verify it yourself with two magnets. Now you might ask, why two poles? Why not 1 or 3 or 17? Well, that is just how it is. That is part of the deep structure of electromagnetism. The magnetic field always forms closed loops. There are no magnetic monopoles, no isolated north or south poles just sitting around by themselves. Every north pole has a south pole attached to it somewhere. Now that is already strange if you think about it. With electric charges, you can have a positive charge all by itself, just sitting there, no negative charge required nearby. But with magnetism, you always get both poles together. If you break a bar magnet in half, thinking you will separate the north from the south, you just get two smaller magnets, each with its own north and south pole. You can keep breaking them into smaller and smaller pieces, down to individual atoms, and you still get both poles. That is telling you something deep about the nature of magnetism. So where does magnetism come from? What is actually happening inside a magnet? Well, here is where we have to talk about electrons, and this is where things start to get truly strange. Every electron in the universe is like a tiny little magnet. It has what we call spin, and because it has spin and because it has electric charge, it creates a magnetic field around itself. Now I have to be very careful here because the word spin is misleading. The electron is not actually spinning like a little ball. It is not rotating in space the way the Earth rotates. The spin is an intrinsic property of the electron, a kind of angular momentum that it just has, that it was born with, that it cannot get rid of. If you try to think of it as a little ball spinning, you run into all sorts of problems. You can calculate how fast the surface would have to be moving to create the observed magnetic field, and you get speeds faster than the speed of light, which is impossible. So it is not really spinning in the classical sense. It is something else, something quantum mechanical, something that does not have a good analogy in everyday experience. But the electron does create a magnetic field. That is a measurable fact. And the direction and strength of that field is related to this property we call spin. Now normally, in a piece of material, in a chunk of iron or copper or anything else, all these little electron magnets are pointing in random directions. Some point up, some point down, some point sideways, and on average they all cancel out. The material as a whole has no net magnetic field. But in certain materials, certain special arrangements of atoms, something remarkable happens. The electron spins can line up. They can all point in the same direction, or at least large groups of them can point in the same direction. And when that happens, when you get millions and millions of these tiny atomic magnets all lined up and working together, you get what we call a permanent magnet. Now, why do they line up? This is where we get into quantum mechanics, into exchange interactions, into the Pauli exclusion principle, and I warn you, this is not going to satisfy your desire for a simple mechanical explanation. The basic idea is this. Electrons are fermions, which means they obey the Pauli exclusion principle, which says that no two electrons can be in exactly the same quantum state. If two electrons are near each other and they have the same spin direction, then they have to have different spatial wave functions. They have to avoid each other more. They have to stay apart. But if they have opposite spins, they can get closer together. Now here is the quantum mechanical twist. The energy of the system depends on how the electrons are arranged in space. And it turns out that in certain materials, in iron for example, the lowest energy configuration is the one where neighboring electrons have the same spin, where they line up parallel to each other. This is not because of magnetic forces between the electrons. That force is way too weak to account for the strength of a permanent magnet. It is because of the exchange interaction, which is a purely quantum mechanical effect that has to do with the symmetry of the wave function, with the fact that electrons are indistinguishable particles that must obey certain statistical rules. I know that sounds like gobbledygook. I know it does not feel like an explanation. But that is because we are trying to explain quantum mechanical phenomena using classical intuition, and it just does not work. The quantum world does not operate according to the rules of the everyday world. Electrons do not have little arrows sticking out of them, pointing in the spin direction. They exist in superpositions of states. They interfere with themselves. They are described by wave functions that evolve according to the Schrödinger equation, and trying to visualize all this in terms of billiard balls or gears or springs is hopeless. But here is what we can do. We can calculate. We can write down the equations, the quantum mechanical equations that describe how electrons behave, and we can solve those equations, and we can predict exactly what will happen when two magnets are brought near each other. We can predict the strength of the force, the direction of the force, the shape of the magnetic field, and our predictions match experiments to absurd levels of precision. So in a certain sense, we understand magnets perfectly. We have a complete mathematical theory that describes them exactly. But in another sense, the sense you probably care about, the sense of having a comfortable intuitive picture of what is going on, we do not understand them at all because there is no comfortable intuitive picture to be had. Now let me tell you why this bothers people, why people keep pushing for deeper explanations. It is because in everyday life, we are used to forces that make sense, forces we can feel and visualize. If I push on a table, I understand that I'm pushing because the atoms in my hand are getting close to the atoms in the table and they repel each other because of electric forces between the electrons and nuclei. That feels like an explanation because I can visualize it. I can imagine little balls pushing against each other, but even that explanation is incomplete. Why do electric charges repel? Well, because they create electric fields, and those fields exert forces on other charges. But why do they create fields? What is a field anyway? Is it a real physical thing filling space? Or is it just a mathematical convenience? And if you push me hard enough, if you keep asking why, I eventually have to say that is just the way the universe is. Electric charge is a fundamental property of matter. It creates fields. Those fields exert forces. That is what we observe. That is what the equations describe. And at some level, that has to be enough. The same thing happens with magnets, only faster. You ask why magnets attract, and I can give you one or two layers of explanation involving electron spins and quantum mechanics. But very quickly we hit bedrock, we hit the fundamental laws of physics, and there is nothing deeper to appeal to, nothing more familiar that I can reduce it to. Now here is where it gets really interesting. Here is where your reality starts to shatter a little bit, because what I just told you about magnets, about electron spins and quantum mechanics, that is actually the easy part. That is the part we understand. There is a much deeper question lurking underneath, a question that goes to the very heart of how nature works. Why are there magnetic fields at all? Why does the universe have this particular structure where moving charges create magnetic fields, where changing magnetic fields create electric fields, where the two are intimately connected in this beautiful symmetrical way described by Maxwell's equations? And the answer, the real answer, is that magnetism is not a separate force at all. It is electricity. Magnetism and electricity are two aspects of the same underlying phenomenon, electromagnetism. And the reason they look different to us is purely a matter of perspective, a matter of how fast we are moving. Let me explain that because it is one of the most beautiful things in all of physics. Imagine you have an electric charge, an electron, just sitting there at rest. It creates an electric field around itself. No magnetic field, just electric. Now imagine you start moving past that electron. From your perspective, from your frame of reference, that electron is moving, and a moving charge creates a magnetic field. So just by changing your velocity, just by changing your reference frame, you can turn an electric field into a magnetic field. This is not an illusion. This is not a trick. The magnetic field you measure is just as real as the electric field the stationary observer measures. But they are not really different things. They are different aspects of the same electromagnetic field. And which aspect you see, how much is electric and how much is magnetic, depends on your state of motion. Einstein figured this out. Special relativity tells us that electric and magnetic fields are components of a single electromagnetic field tensor, and what looks like a purely electric field in one reference frame looks like a mixture of electric and magnetic fields in another frame. Space and time mix together when you change reference frames, and electric and magnetic fields mix together in exactly the same way. So when you ask why magnets work, you are really asking why the universe has this particular relativistic structure where space and time are united, where electricity and magnetism are united, where the laws of physics look the same to all observers moving at constant velocity. And that is a much deeper question. That is a question about the fundamental symmetries of nature, about why the universe obeys Lorentz invariance, about why the speed of light is the same for all observers. These are not things we can derive from something simpler. These are the axioms, the starting points, the deep structural features of reality. You might say, well, surely we will figure out something deeper someday. Surely there is another layer underneath. Maybe. Physicists are always looking for deeper theories. String theory, quantum gravity, attempts to unify all the forces. These are all trying to find a more fundamental description. But every time we peel back a layer, every time we find something deeper, we also find new mysteries, new questions that cannot be answered within that framework. I do not think there is ever going to be a final answer, a point where we can say, aha, this is why the universe is the way it is, and it could not possibly be any other way. I think we will always have to accept some facts as given, some starting points that we cannot explain in terms of anything simpler. And magnetism, electron spin, the structure of electromagnetism, these are pretty close to those fundamental starting points. But here is the thing, and this is what I really want you to understand. The fact that we cannot give you a comfortable, intuitive explanation does not mean we do not understand magnets. We understand them extraordinarily well. We can predict their behavior to incredible precision. We can engineer devices using magnetic fields, hard drives, electric motors, MRI machines, particle accelerators, all of which work exactly as our theories predict. What we cannot do is translate that understanding into everyday language, into familiar analogies, into pictures that make sense to human brains evolved to understand the behavior of medium-sized objects moving at medium speeds in a world dominated by gravity and friction. Our brains were not designed to understand quantum mechanics or relativity. They were designed to throw spears and find berries and avoid predators. So when you feel confused about magnets, when the explanations do not satisfy you, that is actually appropriate. That is the correct response to encountering the fundamental strangeness of nature. The universe does not owe us an explanation that makes intuitive sense. It just is what it is, and our job as physicists is to figure out the rules, to find the mathematical patterns, to make predictions that we can test. And we have done that with magnetism. We have done that spectacularly well. We have equations that work. We have a theory that makes sense mathematically, even if it does not make sense intuitively. And ultimately, that is the best we can do. That is what understanding means in physics. Not a feeling of comfortable familiarity, but a precise mathematical description that lets us predict what will happen next. So why do magnets work? They work because electrons have spin, because spin creates magnetic fields, because in certain materials the spins line up, because quantum mechanics says they should, because the universe has a relativistic structure where electricity and magnetism are two aspects of one thing, because that is the way nature is built at its most fundamental level. Is that satisfying? Probably not. Does it answer your question? Not in the way you wanted. But it is the honest answer. It is the truth as far as we know it. And the truth is that the universe is strange, far stranger than we ever imagined, and magnets, simple magnets that you played with as a child, are your first clue that reality is not what it seems, that underneath the familiar surface lies a quantum mechanical, relativistic, deeply weird foundation that we can describe mathematically but never truly visualize. And that, to me, is beautiful. That is what makes physics worth doing. Not the comfortable explanations, not the familiar analogies, but the discovery that nature is far more interesting, far more subtle, far more strange than we ever dreamed, and that we, with our limited brains and our limited intuition, can still figure out the rules, can still write down the equations, can still understand it in the only way that really matters, through mathematics, through experiment, through the scientific method. That is why magnets work, and that is why your reality should be shattered, because you live in a universe far more magnificent and mysterious than you ever imagined.